This example is broken up into 4 parts. This time we're going to be considering 2 particles that move with their respective position vectors. R1 as a function of time equals r minus 5t in the I direction plus 12t minus 6 in the j direction, and r2t equals 3t plus 1 in the I direction plus 4t minus 4 on the j direction. And we're told time is measured in hours and the distance is in kilometres. So we're asked to find the initial position of each vector. So initial position, that is the starting point, that is where time is equal to 0. So taking our first position vector, r1t, I substitute 0 where t is. So I get 3 minus 5 times 0, which comes out to be 3 in the I direction, plus 12 times 0 minus 6, which comes out to be negative 6 in the j direction. Similarly, I do the same for my second position vector, r2t. I substitute 0 for t, so I get 3 times 0 plus 1 in the I direction, which comes out to be 1i. We do not need to write the 1, plus 4 times 0 minus 4, which comes out to be negative 4 in the j direction. So I now have the initial position of each particle. Part B of the question again asks us for an initial distance, and an initial distance t equals 0. So we have found their positions in part A, and we're going to use that information to help us with part B. What we have from part A is 2 position vectors. R1t was equal to 3i plus 6j, and r2t was equal to I minus 4j. So what we need to do is find the distance between the 2. This is going to be using some of the material that you have done earlier on in the year. I'm just going to do this theoretically first, and then I will use my position vectors. I'm going to draw 3 points on my screen: O, P, and Q. The position vector to point P I've drawn in, and the position vector to point Q I've drawn in from point O. What we want to do is find the distance from P to Q. That is the distance between the 2 vectors. Now we know to add vectors together we have to join them head to tail, and that is not the case here. So we know vector PQ is equal to vector PO plus vector OQ. Our problem here is our vector goes O to P, not P to O, so we can rearrange that to being OQ minus OP. So OP I have called position vector for 1, and OQ the position vector for R2. So what I now have there then would be R2 minus R1t. I have a problem. I've been asked to find distance. But if you remember from back in the earlier work on vectors, we can say that the magnitude of PQ is equal to the magnitude of vector R2t minus R1t. That is what I've written for distance. Combining those together, 1i minus 3i gives me negative 2i, minus 4j minus 6j gives me 2j. And I'm going to take the absolute values of these using the relationships you used earlier on in the year. That is, I'm going to take the negative 2 and square it, and the 2 and square it, all within a square root sign. Negative 2 squared is 4, 2 squared is 4, 4 plus 4 is 8, so it's the square root of 8, which is 2 root 2, and the units we were using for distance was kilometres. In part C of the question, we're asked to find when and where the particle meets. So there's a few things to consider there. When, that's time. Where, that's position. So, it is possible for two particles to cross a path of each other but at different times. Then they won't meet. When they do meet, their position has to be the same for both x and y, and that time has to be the same when they're at that position. So what I've done is I've equated the two position vectors that I have. Now, what should happen here, if they're at the same place at the same time, their x components must equal each other. So 3 minus 5t must equal 3t plus 1. And then I have solved that. 8t equals 2, t equals a quarter. Now, for them to be at the same position at the same time, I must get the same value for t for my j component. 12t minus 6 must equal 4t minus 4. That gives me 8t equals 2, t equals a quarter. So their x values and their y values were the same, both when t equals a quarter, so they met there. Now the units for time that we were given was hours, so 1/4 of an hour is 15 minutes. So I can take my t equals a quarter and I can substitute it into either position vector. It doesn't matter which one, because both of them will be at the same place at the same time. So substituting the t equals a quarter into one of them, I've used R2 here. I get 3 times a quarter plus 1, which is 7 on 4. And I get 4 times a quarter minus 4, which is negative 3. That tells me that the point at which they meet is the point 7 quarters, comma, negative 3. And they do that after 15 minutes. If there was not a solution, then as you can see what I have written, if they do not have a solution, that was the same. They would never be at the same place at the same time. that doesn't stop them being at the same place but at different times. The last part of the question asks us to find the Cartesian equations. So with R1t, we know x is equal to 3 minus 5t. So I can get t by itself, which gives me 3 minus x over 5. I can do the same with y. Y is equal to 12t minus 6. Rearranging that to get t by itself, I get y plus 6 is equal to 12. I've got my expression in terms of x equals t, my expression in terms of y equals t. Because they both equal t, they must be equal to each other. Now what I do is tidy it up. I can times my left hand side by 5 and my right hand side by 12, and I've expanded those brackets, giving me 5y plus 30 equals 36 minus 12x. Now I've got an expression where I've got 5y plus 12x, because I've taken the 12x across, equals 6, because I've taken the 30 across to the other side. So I've got an equation of straight line. Similarly, for R2t, I know the x component is 3t plus 1. I can rearrange that to get an expression for t. I know the y component is 4t minus 4. I can rearrange that to get an expression for t. So those two expressions must equal each other. So y plus 4 all divided by 4 must equal x minus 1 all divided by 3. Now tidy it up. And a little bit of algebra gives me 3y minus 4x equals negative 16.